So, to increase the delay, so delay can be increased further by putting some further instructions. So, one possibility is that we can increase the count value of this register pair that we are putting into. So, that way delay will increase significantly. Sometimes what is required is that we can we do not need that much increase. Okay. So, it may be just very small amount of delay has to be inserted. So, for that purpose, so we can put some instruction which does not have any effect. So, like this NOP type of instruction. So, another, so we can think about different NOP type of instructions, like you can say I put an instruction like move b comma b. So, effectively it does not have any operation that it is doing. So, it does not do any computation or any movement as such. So, that way it is similar to the NOP, but anyway, so this NOP is much more understandable. So, that way many a time we put these NOP instructions inside the delay loops to increase the delay. Next, we will be looking into something called the timing diagram. So, this timing diagram, this actually tells that when are the different control signals generated as we are proceeding through the operation of instructions. So, following buses and control signals must be shown in a timing diagram. If we are drawing the timing diagram of 8085, so we must show these lines: a higher order address bus, lower order address bus and data bus, then the ALE signal, the read signal, write signal and IO M bar line. So, these are the minimum signals that you must show when you are asked to draw the timing diagram of any 8085 instruction, because that will tell us how are the things going on inside the processor for executing the instruction. So, let us consider this instruction move a comma b. Okay. So, here the opcode is is 78. So, this opcode how this will be done. So, this is, we assume that this instruction is at memory location A000 hex, and at the, so if you can say that if this is the location A000 hex, then here the 78 is available. Now, how is it going to be fetched to the processor and going to be executed? So, that we will see. Now, so this is the timing diagram for for this execution of this instruction. So, in the first clock cycle, so this requires only 4 clock cycles, which forms the part of this opcode fetch cycle. So, in the, so this is the address bus content. So, this A15 to A8 higher order address bus, it contains the higher order part of the address, that is A0, and the next part, so this lower order address part A0 to A7, so they are contained in this lower order address bus cum data bus. So, that is the 00 hex, and when this lower order data is lower order address is available on the lower order address bus, this ALE signal is activated. Okay. So, this ALE signal is activated, as you know that there is a latch outside the processor, and it is expected that this if this is your if this is the processor, and then there is a latch here. So, this lower order address bus comes here and the ALE signal goes there. So, ALE signal is used to latch this lower order address bus, and then if this is the memory, then this lower order address bus and the higher order address bus together. So, they form the address for the memory, and the data comes to the data bus directly like this. So, we have got this ALE signal activated here, and this ALE signal is activated when the lower order address data bus, it contains the lower order address part. So, the process, so now to the memory, the address has been given properly. Now, since this is a memory read operation, so fetch is a memory read operation. So, this read bar signal is activated at the beginning of T2. Okay. So, during T1 ALE was active, during T2 this read bar signal is active. So, this read bar signal goes low telling that it is asking for the instruction or the data from the memory, and getting this read bar signal. So, again if this is the CPU, this is the 8085 CPU and this is the memory. So, so far we have been able to set the address bus and we have been able to give the read bar signal. So, when we give this read signal, then the memory will put the data onto the data bus, which happens to be the lower order address bus itself. So, this 78 value, which is the content of the location A000 hex, is put onto the data bus, and then this processor will read it from the data bus. Now, the write bar signal, since this is not a memory write operation, so this is kept continually high throughout the operation, and this IO M bar signal, so this is made low because this is a memory operation and not an IO operation. So, that way this opcode fetch opcode fetch cycle is executed for the MVI instruction. So, if you draw this timing diagram, this tells us explicitly how different control signals are being activated by the processor to get the operation done. Let us take a slightly more complex example, MVI A, 45 hex. So, here you can understand that in the first machine cycle, so is the fetch machine cycle, and in the fetch machine cycle, so it will fetch the instruction, and since it can fetch only 8 bit of data at a time. So, if it will in the first cycle it will get the opcode part. This MVI A 45 hex, this instruction, so this instruction has got a coding of 3E for the MVI A part, and the next part is 45 hex. So, if the instruction is again at location A000 hex, so it will take 2 bytes to hold the instruction. So, location A000 hex will have 3E and A001 will have 45. Now, the way the operation is done is similar, like it is in the opcode fetch cycle, it is similar to the previous case. So, this higher order address bus contains A0 hex, lower order address bus in the first clock cycle contains 00, the ALE signal is activated, and then this, so when the ALE signal is activated, then this 00 gets latched onto the memory on the address bus of the memory. So, we have got the memory address bus contains A0000 hex, the total 16 bit address. Now, read bar signal is given. So, the memory will put the content of that location 3E onto the data bus. Now, the processor, so a write bar signal is high and IO M bar signal is low, that is as previously. Now, getting this 3E, the processor understands that okay, the controller part, the instruction decoder and the control unit. So, it will understand that this is a MVI instruction, MVI, so MVI A instruction. So, for that it needs to get the immediate value. So, it has to read the memory once more. So, that is the it has to go into a memory read cycle. In the memory read cycle, it is similar to the fetch, but 1 T state less than the fetch. So, it is putting this higher order address bus, higher order address onto the higher order address bus, lower order address onto the lower order address bus, and it is giving the ALE signal. Now, so this address part gets latched to the address bus of the memory, and then it gives the read signal. So, in response to that, the memory will put this 45 hex onto the data bus, and this 45 hex comes to the processor. Okay. So, this way this 45 hex, so this I get this value into the memory into the processor, and the processor will now put this 45 hex into the A register. That is done immediately after the 45 hex value has been obtained. So, it is put immediately into the A register. So, it does not require any more clock cycle. So, one interesting thing to note is that this fetch and this memory read. So, both these cycles are similar. So, both of them are doing some sort of memory read operation, but in case of opcode fetch cycle, it takes one T state more than the memory read. So, this is most probably due to this decoding operation that the processor has to do after getting the opcode part. Though it is not documented in the manual, so it is not very difficult to understand that the decoding takes some time, and this extra clock cycle that is put in the opcode fetch cycle. So, that is most probably for doing that decode operation carefully. So, that is the timing diagram of this MVI A type of instruction. Next we will look into another instruction which is LXI instruction. So, LXI B comma F045 hex. So, that is that is a 3 byte instruction as we know. This LXI B, so its opcode is 21 hex. Then this F045, so 45 will be put at location A001 hex and F0 will be put at A002 hex. So, this is the 3 byte coding of this instruction. Now, how is it going to be executed in terms of timing diagram? So, we would like to see. So, this is the whole operation. So, we start at first this higher order address bus contains A0, lower order address bus contains 00, ALE signal is given. So, and this read bar signal is given. So, this memory will get the content of this location, that is 21 hex, and put it onto the data bus. So, here, so put it onto the data bus when the read bar signal is low. So, this write bar and IOM bar both are write bar is high and IOM bar is low, because this is not a memory write operation and this is a memory operation. So, that way. So, after that, so this T4 is for the decoding part. So, in the T5 clock cycle, so it will understand, the processor understands that okay, now I have to, this is a code of LXI, this 21 hex is the code of LXI, it is the code of LXI B instruction. So, it has to get 2 more bytes and accordingly initialize the B and C registers. So, it will do that. So, it will put the higher order address part A0 onto the higher order address bus. It will put the lower order address part 01 hex onto the lower order address bus, give the ALE signal, and then it will give the read bar signal. So, as a result, memory will put this 45 hex onto the data bus, and then this 45 hex comes to the processor, and the processor puts this 45 hex into the C register, because that is the lower order byte. So, that goes to the C register. After that, it comes to the next memory read cycle, where again it puts this A0 hex onto the higher order address bus, 02 hex, this the next address is put onto the lower order address bus. Actually, this constitute the program counter. So, this higher order address and this lower order address, it combines together into the program counter register, and after every memory fetch or this memory read operation, so this program counter is implemented. So, that way it is doing this after every fetch. So, this is an instruction fetch operation that is going on. So, till the instruction complete instruction has been fetched, this program counter value goes on implementing. So, that is it becomes A002, and this A0 is put onto the higher order address bus from the PC high, and this 02 hex, that is from the PC low, that comes to the lower order address bus. And similarly, when this ALE signal is given, so address is latched, and when this read bar signal is activated, so this it is read from the memory. So, this F0 hex value that comes from memory, and it is loaded into the B register. So, this way this LXI B instruction is executed, and we have got all entire timing diagram. So, that illustrates how this LXI B is done. Next, we will look into another interesting instruction, which is move A comma M. So, this is slightly tricky, because you see that the meaning of this instruction is that your this content of memory location pointed to by HL register pair will come into the accumulator. So, the corresponding code for this is 7E. Okay. So, this is 7E, and how this instruction is going to be executed is like this. First, it has to get first part is same. So, that is the opcode fetch cycle, and for the opcode fetch cycle, so the A0 and 00 they are put onto the address bus, ALE signal is activated in T1, read bar is activated in T2 and T3. So, this is we get the value 7E into the instruction decoder. Now, this instruction decoder finds that this is an move M A comma M instruction. Now, it has to start a memory write operation. So, sorry, this is a memory read operation, because content of that memory location will come to the A register. So, that is a memory read operation, but how, what is the higher order address now? As I said that in move A comma M instruction, the address is given by the HL pair. So, this H register pair value goes to the higher order address bus, and L register value goes to the lower order address bus. So, that way, and the ALE signal is generated. So, it is this value, this address is latched, and then the read bar signal is given, so that the content of the memory location pointed to by HL comes to the data bus, and then when it comes to the data bus at the end when it is available, so the processor will put the value into the A register. So, this way it goes into an opcode fetch cycle followed by a memory read cycle. The other way, the move m comma a, so that is another operation where we are trying to use this indirect addressing, and here the content of the accumulator register will be saved onto the memory location pointed to by the HL pair, and the coding for this is 77. So, that is available from the manual of 8085, that the code for a move m comma a is 77 hex. So, how is it done? So, initially we put this higher order address bus contains the A0, lower order address bus contains 00, and then ALE is given in the first clock cycle, read bar is given in second, third. So, as a result we get the instruction 77 into the sorry, this value should be 77, not 7E. So, this comes to the data bus, and then the processor will understand that this is a move m comma a instruction. So, then it will do a memory write operation, because now the content of the A register should be put onto the memory. So, this address of that memory location is given by the HL pair. So, this H register contains the higher order address part, L register contains the lower order address part, ALE signal is given to latch this L register value to the lower order address bus of the memory. Then you see the write bar signal has been made low. So, write bar signal has been made low, and the content of register A is put onto the data bus by the processor. So, the memory when it gets the write bar signal, so it whatever is there in its data bus, so it will write it onto the memory location pointed to by its address bus. So, that is done. So, content of that location comes to the content of A register goes to that particular location pointed to by the address bus of the memory. So, to summarize, we can say that so far we have seen different types of cycles. So, these cycles they are known as machine cycles. So, there are different types of machine cycles that we have seen. The first one that we have first machine, any instruction to start with, so it has got a fetch cycle, okay, or opcode fetch cycle. So, that is common for all the instructions. So, after that, so there may be a number of memory read, it can be a memory read, it can be a memory write. So, this type of cycles can be there. Now, this fetch cycle, so it takes 4 clock states or T states, whereas this memory read and memory write cycles, so they take 3 clock cycles. So far we have got introduced with 3 different types of machine cycles. So, we will see some more as we proceed. Okay. So, these machine cycles are used for these machine cycles are actually part of this is a combination of these basic clock cycles or T states, and that way it constitutes different operations to be done by the processor. Next, we will be looking into another very important aspect that we have in any processor based program execution, that is called the stack. So, if you think in terms of the architecture or organization of the system, then the stack is an area of memory identified by the programmer for temporary storage of information. So, we very often we we want to have some space where we do some bookkeeping job. So, we keep some temporary data. Okay, so that we can put it in we can do it with the stack. Stack is a last in first out structure, because in case you may be familiar with stack as a data structure, where there are 2 operations, push and pop, and this push operation it puts the element onto the stack, and the pop operation, so it takes the element out of the stack, and this always operates in a last in first out formulation. So, stack normally grows backwards into the memory. So, what we mean is like this. So, if this is the memory, okay, if this is the full memory. Now, so this is the address say 0, say if I have got a 16-bit address bus, so that goes from 0000 to FFFF, so total 64K space. Now, you can say that out of that my stack it will start at this location. So, this is the location say 8000. Now, normally what happens is that the stack starts growing from this point and it grows towards the upper side, it goes towards the 0. Of course, that is the convention only, but the way these stack manipulations have been implemented in 8085 processor, it happens like this, that it grows backwards up to towards the lower and lower addresses. So, programmer, as a programmer you can define the bottom of the stack, and from that point onwards it can it grows up by reducing the address value. Okay. So, this is the stack operation. Now, we will see how this happens in the 8085 instruction in the 8085 processor. So, given that the stack grows backwards into memory, so it is customary to place the bottom of the stack at the end of memory to keep it far away from the user programs. Like in the previous example, I said that my memory ranges from 0000 to FFFF and I put the stack to start at 8000 hex. Now, there is a possibility that some user program data will clash or program code will clash with that stack. Just to avoid it, so this may be a safe practice to have the stack initialized at the very bottom of the memory. So, this stack may start at this FFFF hex, and in 8085 the stack is defined by setting one special register which is known as the stack pointer register. This is a 16-bit register used for accessing the stack. So, what we want is that if this is my memory, and then the last address is say FFFF. So, I want this FFFF to be the stack to be the beginning of the stack. So, for that purpose we have to initialize the register SP to the value FFFF hex, and for that we have got this instruction LXI SP comma FFFF hex. So, the stack pointer gets initialized to the end of the last memory location. So, from that point onwards it starts growing and it can grow towards the address 0. Now, how can you save or retrieve data information from stack? Information is saved on stack by pushing it on. So, you can push a data onto the stack. So, that will be saved onto the memory locations pointed to by the stack pointer, and then you can retrieve it by doing a pop operation. So, push and pop. So, these are the two operations for writing and writing to and reading from the stack. 8085 provides two instructions similarly, push and pop. So, if you look into stack as a data structure, so you will find that it defines two operations, push and pop in the stack, and similarly here also we have got this push and pop as two instructions in the 8085 processor. So, they push and pop, they work with register pairs only. So, you cannot push or pop a single register, an 8-bit register. So, we have to work with this register pairs. For example, push B. So, when you do push B, then this push, so this actually means we are trying to save the register pair BC onto the stack. Okay. So, we cannot have an instruction like push C, because push C is not a register pair. So, B is a register pair consisting of the registers B and C. So, we cannot have an instruction like say push, push C. So, this is not possible, or say push E, say push L. So, this is not possible. So, these are not there. Okay. Now, so how is it executed is like this. See, I have got a stack. So, this is the memory, and then suppose at present the stack pointer is somewhere here. So, stack pointer is pointing to this location, and this is towards the address 0, lower address. Now, if I am executing this push B instruction, so what I want is somehow these B and C register values will be saved onto the stack. So, what is done? This stack pointer is decremented. So, stack pointer now points to this. So, stack pointer now points to this location, and then copy the content of register B to the memory location pointed to by SP. So, at this location we copy the content of B register into this, and then we decrement the stack pointer further. So, stack pointer now points to this location, it points to this location, and there we copy the content of the C register. So, this way it operates. So, when you say push B, it first decrements the stack pointer, then copies the content of B register onto that, and then decrements the stack pointer further, copies the C register content. So, you remember that in case of 8085, this lower order byte is always stored in the lower order address location. Now, out of this BC register pair, so C is the lower order register, so and B is the higher order register. So, this lower order register has gone to the lower order memory address C, and this higher order address higher order register has gone to the higher order register higher order value. So, that is the higher order memory location. Okay. So, this is always true. So, so when you are doing a save, saving some copying some 16-bit value into some memory location. So, this is done the other way. Okay. First this higher order is copied and then the lower order is copied, but that is sorry, first the lower order is copied, then the higher order is copied. But in case of stack, since stack grows in the reverse direction, it is going towards 0. So, this lower order register is copied later. First the higher order is copied and then the lower order is copied.